Okay, getting to new slides. So dividing up water, we're going to have one of the first things we'll do is separate the water from the dry matter. So we can represent that visually with this graph. That line there between the blue and the red is going to vary depending on the feed stuff, but we just did that division so everything kind of fits in. We look at water or moisture in the feed and then dry matter. If we take the water plus the dry matter, we're looking at as fed. So the feed as fed. One of the challenges of working with ruminants is we balance rations on a dry matter basis, but we feed on an as fed basis. So we need to be able to go mathematically back and forth between dry matter and as fed when we're looking at our cows. So most of the time we're talking about feeds, we're only talking about the dry matter portion, but what the animal consumes is that dry matter plus water as we go through, and that amount of water varies depending on the feed we're dealing with. So we have the feeds, I'll list here. You have this thing in the handout I just gave you, and then the approximate water content for those feeds. If we're dealing with grains, they're air dried. In this part of the country, air dry gets us down to about 10% water. We go out to Arizona, particularly this summer, we might get down to 5% water. But in the Northeast, we're hot and humid. We're looking at 10%. Good hay is going to be 10% water, 10% moisture as we move through. If we're going to do a good silage, depending on the system we're in, we got to get that moisture right for the system we're doing. Ranging typically 55 to 65% water. Bunker silos, we're going to be a little drier. Upright silos, a little wetter in bunker silos, a little drier in upright silos. If we're dealing minerals, just taking them out of the bag, we're doing something less than 5% moisture. So has anybody opened that salt bag and it flows freely? That's usually like 99% dry matter. The salt that sits there for a while, gets cakey, gets gushy, is going to be something greater than that. Those mineral bags, typical pasture, about that tall, is probably going to be about 80% water. Not the green lush short stuff, which will be 95% water. Not the old grown out stuff will be more like 10, 15% water. So that average kind of 16 inches of growth will be somewhere around 80% moisture. So how is water determined or dry matter determined? When we're looking at a feed, the amount of water percentage plus the dry matter percentage has to add up to 100%. So one plus the other will give us 100%. So typically what we'll do is we dry at a variety of different temperatures and different methods. So there are different ways to look at this depending on what we're trying to do. So Coster runs about 55% C, 55 degrees C. This is, we use that temperature, get us in there a little bit more, a little bit quicker. This is, we're trying not to drive off the silage acids by overheating it. If we're working in a lab, we'll use 100 degrees C. What do we know about 100 degrees C?
Boiling point of water, right?
It's a boiling point of water. So in theory, we're boiling all the water off. If you do it right, you're going to do a procedure called hot weighing. You'll take that beaker that's got the feed sample in there. You're wearing gloves. You'll take it out of that 100-degree oven. You'll put it right on the scale and weigh it right there. Because if you let it sit, it will absorb water back. The glass will also absorb water. The Pyrex in labs will also absorb water. So you have to do some hot weighing before and after, and a lot of tears have to be there. But if you're going to get it right, there's a multi-step, and that's why we have Excel spreadsheets that capture these things automatically. We can do it with a coster. You guys will be learning how to do that, along with the other methods. We're going to show you how to use a microwave to do dry matters. So costers, the nice thing about them is you can turn them on, get them running. You can walk away until they're done. Microwave is a lot shorter. You can do one in probably 10, 15 minutes, but you cannot leave. Because as we demonstrate every year, somebody sets the feed sample on fire. Everybody's done that with a hot pocket, right? You get down to that last thing, you've gone a little bit too far. So we'll show you how to do that and tell you what to do if it does catch on fire. We'll also use a dehydrator. Sometimes we use this for sample prep. This is a lot easier to do with large samples. So there's limits on sample size. There's sampling errors associated with each of these methods. There's time constraints. There's different approaches to what we're doing. So those are various methods where we're trying to boil off the water with some form of heat. There are probes that will measure conductivity or resistance to electrical flow. So the more water there is in the feed stuff, the more electricity should flow. And if we can correlate that with a known amount of water, we can get our estimates for that. I know we got a lot of grain probes that'll do this for us. They're not really good for hay and things like that, but they're better than nothing, I suppose, most of the time. Another measurement we'll use and we'll talk about is near infrared reflectance, NIR. When we send in our feed samples, we say, do we want wet chemistry or do we want NIR? NIR puts a particle beam through the feed stuff and measures the pattern of scattering. You take a set of known standards, and this scatter means there's 20% moisture in there. This scatter means that there's 30%. So it's only as good as your standards, and in your lifetime, this will get pretty good. The bank of standards has been growing pretty much steadily for the last 20 years. So we're getting all kinds of different patterns, and we can use them to get that done. If you've really got a small amount of water in a feed sample and you really want to get it absolutely accurate, toluene extraction is the way to go. You're taking the carcinogen toluene, you put your sample in that, and that extracts the water out. You measure the change in volume before and after your feed stuff goes in. How much water is pulled out with that toluene, and then you can back calculate given the weights that you're dealing with. So separating water from dry matter. This is not an easy thing to do. If we're looking at the drying processes, which are the ones we'll be dealing with in this class, water does not want to separate. So our goal with drying is to drive off all of the water, but yet leave all of the dry matter. And that's never a clean thing when you're doing it, especially when you're dealing with silages. You're going to start to drive dry matter over the hotter you get. water tends to be sticky, so it does not want to let go of things. So the more heat we put in there, the more dry matter we put in there, the harder that water wants to stick. We also don't want to get it so hot that we start to burn the dry matter. If we burn, respire, and then what happens? Where's that dry matter go? Ooh, right? Goes up in the air. If we're doing a measurement, we burn the dry matter like we might in a microwave. We burn that dry matter, and then we weigh our sample again. What have we done? We've overestimated the moisture, underestimated the dry matter, because we assume that water just disappears, but if dry matter also disappears, we are going to underestimate our dry matter. So the challenge with water is it likes to stick to everything. And that's one of the cool properties of water. That's why it flows through a paper towel when you put it down on a spill. It sticks to everything. It wants to be there. But trying to separate things out is a challenge when we're doing that. So we tend to make some assumptions. It's very hard to separate purely and cleanly. Water over here, dry matter over here. So we accept a certain amount of error. If you take a Coster dry matter at 55, 60 degrees Fahrenheit, that's going to be a greater dry matter than if I did it at 100 degrees. There's still some water in that Coster sample that would be driven off if we did it at a hotter temperature. But we accept those things. We get patterns. We get, okay, this is a measurement I can deal with. I can work through it. So you'll get an opportunity to do this on Thursday. We have the drying time across the bottom. And then say we start out with 100 grams of sample. We add heat to it. We start losing water. At some point, we'll come to a plateau for that temperature where all the water is driven off. Depending on the system or what we're working with, there's a potential that if you keep it running, you're going to start to burn off dry matter. So this all appears water in the sample. This is dry matter. The measurements, as we go down, we are starting to burn off dry matter. And this will happen with a microwave if we let it run too long. So when we're taking our dry matters, we're looking for that plateau, wherever that is. And you'll see that it's not a perfect plateau. It's not necessarily a smooth curve, especially as we get toward the end. Things bounce up, things bounce down. But we'll demonstrate that on Thursday. So dividing up feeds into nutrients. The first step is to separate water from dry matter. Now, once we have that sample dried, we grind it, and then we analyze that dry matter. So the stuff you can hold in your hand. This is where all the other nutrients are. We need to be able to measure them in some way. So if we're looking at 6 nutrients, we have water, carbohydrates, protein, fats, minerals, and vitamins. And this is more or less the way we're going to go through things this semester. So we're working on water. We're going to move over to carbohydrates today, or at least introduce them, and then get on to protein, fats, minerals, and finish the semester with vitamins. So focusing on that dry matter side of things, we take the sample, we dry it down. Once it's dry enough, we can run it through a mill that grinds it down. So we usually grind it to pass through a 1 millimeter screen. So we're looking at something that's very, very small at the end. So powder, close enough. And then once we have that sample prepped, we can start to do our measurements to measure those different fractions. the carbohydrates, the proteins, the fats, the minerals, the vitamins. And we usually do them, if we're doing wet chemistry, we do one assay at a time. If we're going to do protein, we'll do a hot nitrogen. If we're doing fats, we'll do an ether extract. If we're doing minerals, we'll do atomic absorption. So more often than not, the sample is destroyed as well while we run this assay. We can't use it again. So if we're collecting samples to do analysis on, we're probably going to need 10, 20 grams to do a standard nutrient profile. But as we said before, that sample, that 1 or 2 grams is just that teaspoon that sits in the palm of my hand. That goes into the hock, that goes into the fiber, that goes into the ether extract. Then based on that, there's usually a difference. How much weight was there when we started? How much weight was there when we finished? Or there's some sort of reading that we'll take or measure, and then compared to standards, we calculate our results. What percentage by disappearance or remaining is that feed fraction? How much color is there for a hock? How much absorption in the flames for minerals? To calculate our results. So there's a lot of weighing and there's a lot of meticulous things. The 2 categories for analyzing dry matter, we're going to focus on traditional wet chemistry, which is what's certified by the National Association, AOAC, a National Organization of Certified Chemists, I think it's something like that. But they have procedures that are related to the labels. Everybody look at a label and say minimum X amount of fiber, maximum amount of salt, minimum amount of energy. Those analyses are determined by the AOAC. We'll also do near infrared reflectance, NIR. This is traditionally more accurate. This is a whole lot faster. And sometimes we want speed. Sometimes we have to have accuracy, depending on what we're dealing with. So if we look at wet chemistry first. Wet chemistry, we think of beakers. We think of Erlenmeyer flasks. We think of scales. All kinds of that lab equipment. Anytime they see, well, we're going into a movie, we see we're going into a lab and they always have something bubbling. I've spent a lot of time in a lab. It's rare that we have something bubbling, but that's usually we're running an assay. So wet chemistry. There are actual chemical processes being run and we figure out what's there and what's not. So we may put the feed in that glass container, the beaker or flask. You're going to add chemicals. You're going to add solutions to that flask or that beaker, that glass container, and then you're going to measure what happens. What colors are generated? What disappears? What remains? Trying to measure things out. The pluses of this wet chemistry, it's very well standardized. There are a lot of people that came together to agree this is how we're going to do starch. This is how we're going to do NDF. This is how we're going to do proteins. This is how we're going to do amino acids. This is how we're going to do fats. Everybody came together and said, okay, and those methods are listed in a very large handbook. They're updated every few years. They're standardized and very reliable. We can get the same measurements over and over again. The downside to that is they take a lot more time generally. To do a fiber by wet chemistry, I have to get my sample dry and prep. That takes at least 12 hours. Then I can run it through an NDF. That takes an hour. I put it through a filter. I put it back in the drying oven. It's got to stay there for at least 12 hours. Then I'll weigh what's in that gooch crucible. Then I'll put that crucible in an ash oven to correct for ash. That's going to take 6 hours. Then I got to take those gooch crucibles and put them back in a drying oven. So I got to measure everything 3 times. The shortest I was able to compress that down is 48 hours. I guess I could have stayed there, but when we're running a research trial, knowing what that NDF is accurately to change our rations, to adjust our rations, the shortest I could get it done from wet sample to answer was 48 hours. Now, there was a lot of waiting, putting it in there for 12 hours, putting it in there for 6 hours. I can go do other things, but the processes take time. So money, there's usually more money associated on a variable cost. You've got labor, you've got chemicals, you've got time to wash glassware. The best guy at Michigan State could do 32 NDFs at a time. 8 racks of 4, he could manage those. I could only do like 16. He was a whole lot better, there was no wasted motion in what he did. On a good day, he could run maybe 150. So you've got somebody's full day salary, all the chemicals, all the electricity, all the equipment associated with that. So that fits into labor. These things take longer, they take more time. And sometimes we have to do it. So near infrared reflectance, NIR. What do we do there? We've prepped our sample, dried and ground. We're going to shoot a beam through it. Then we measure the pattern generated by the chemical bonds in the feed. We look at that pattern and say, oh, that's protein, that's carbohydrates. So it can do water, it can do all kinds of organic things there. It cannot do minerals. So that's an important thing to remember. So once we look at that pattern that's generated, we compare it to a standard set of feeds that has been through wet chemistry. This is what a 20% crude protein feed looks like. This is what a 15% crude protein feed looks like. This is what a 5% fat feed looks like. And it compares things. So it's only as good as its reference set. Once you've paid for this NIR, it's really fast. You're done. It's a big, expensive machine, but it can do thousands of samples in a day. Get them in their disk, load them up, just go one right after another. So a lot of testing things are going to go through that fast and cheap process. I don't have the chemicals, I don't have the labor, I don't have the time. I don't have the materials that need to be there. I don't have multiple pieces of equipment. I just have one. So after startup costs, negatives, as we mentioned already, it's only as good as its reference set. When we're starting out, there were a lot of weird feeds that don't do real well. And you'll still see when you send in an NIR, if it's out of range or does not fit the reference set well, they will still go back and do wet chemistry to double check things. We agree or disagree with what the NIR said. There needs to be chemical bonds to run this. So the downside of this is there's no chemical bonds associated with minerals. NIR will give you answers to minerals. There'll be numbers in the space, but they're completely bogus. I could make them up and they'd be just as accurate. They're fast, but they're garbage. So if you're doing NIR, you disregard the minerals unless you ask for a specific mineral package that measures things accurately. There was a thing in grad school. It's like, well, why don't we start an analysis service where we have an immediate turnaround. You email me in, I'll send you numbers back. Got immediate analysis. I made the numbers up, but you got fast turnaround. Just because they give you a number, you need to critically look at it and make sure that those numbers mean something. When you're doing NIR, you need clean or unmixed samples. It does not do well with a TMR. It does not do well with mixed forages. It's only as good as its reference. So they're getting better and better with the mixed forages, but TMRs, I would not trust a NIR. There are no good references that are going to match my TMR well. So it's great for grains, great for pure alfalfa stands, pure grass stands, but we kind of get a little foggy when we get into mixed things. So we're looking for clean or unmixed samples. They're going to give us the best results. And again, you have to decide what you want out of this. Is a number to the nearest 5% good enough? Or do you need something to the tens place or the hundreds place? Sometimes nearest 5, I'm good. Especially when we're doing dry matters, when we're doing stuff on the fly. Of course, now the choppers all have dry matters in them. Doing that conductive resistance sensors through. I know they were trying to put some NIR. I don't know if they're in there yet. NIR sensors directly in a harvester. But on the fly, doing costers, if I do them in 30 minutes, I get to the nearest 5%. I know whether it's dry enough or not. Doesn't have to be exact. Versus if I want my minerals, I might want a decimal place or two, especially if I'm dealing with my dry calves, to be accurate. Any questions on separating water from dry matter? Literally crickets, right? Crickets and tumbleweeds, right? Okay, get out your letters. What likely increases water intake? A, eating less feed per day. B, eating more salt per day. C, producing less milk per day. D, eating wetter feed. So we're looking at drinking here. So eating more salt is going to increase that water intake. Where doesn't her daily intake of water come from? Drinking it, eating it, metabolism or respiration in body, the newly remodeled Dollar General. So Dollar General, remodeled recently. Got all kinds of new freezers in there. So moving on to carbohydrates. What do you guys know about carbohydrates? Anything?
They can be simple or complex.
They can be simple or complex. Anything else?
Glucose and sugars are carbohydrates.
Sugars are carbohydrates. Okay, carbohydrates. Carbohydrates. The name comes from the chemical formula. When they initially analyzed things, they found that there's one carbon per two hydrogens per one oxygen. If you look at that, H2O is water. So they said carbon hydrates, carbon water is where the name comes from. Is that at all related to what's actually there? No, but that's where the name comes from. So the ratio of one carbon atom to two hydrogen atoms to one oxygen. And that ratio roughly holds, depending on how big those carbohydrates are, depending if it's 7 carbons, 8 carbons, or 3 carbons, that ratio might slip a little. But overall, we're dealing with things that have carbon in them, hydrogen, and oxygen. Not dealing with sulfur, we're not dealing with nitrogen, we're not dealing with phosphorus. So carbohydrates, we start with the monosaccharides. We've already mentioned glucose, the end product of photosynthesis. We can rearrange that glucose. If anybody here likes Legos, you take something off here, you put it over here, switch things around. We can generate a 6-carbon compound called fructose. Galactose, we take glucose, we rearrange it, it's a galactose. Anybody know where galactose belongs? We look at galactic, what does that mean? Galaxy. That's not where we're going. We're going with lacto. Where's lacto?
No.
Milk. Milk sugar. So this is half of milk sugar. But all of them have 6 carbons. All of them have that 1:2:1 ratio. They are just rearranged differently in space. We look at glucose. Each of these letters represents an atom. So we have 6 carbons in a chain. So this is the chain version. This is the ring version. If we look at 1, 2, 3, 4, 5, 6 carbons, we'll have 1, 2, 3, 4, 5, 6 carbons in the ring. So we have the 1 carbon reaches around to the 5th carbon to close that ring. So we have an oxygen in that ring through what's called an ester linkage. We don't really need to worry about that too much. But glucose, 6 carbons is where we want to focus. Next step up is we take 2 sugars and stick them together. We get disaccharides. The way we used to talk about. They used to be saccharides. Sucrose. Does anybody know what sucrose is? Table sugar, what we have on our table. That is a fructose and a glucose stuck together. Lactose. Anybody know what that is? No. Milk sugar. That is a glucose and a galactose stuck together. Maltose is 2 glucoses stuck together. It's either the breaking apart or the building up of a complex carbohydrate. You're doing it 2 steps. So to make table sugar, take our glucose, our fructose, put them together. We have our disaccharide, table sugar. Lactose, and glucose stuck together. You got that oxygen in the middle that brings them together. Last thing we'll deal with in this class, we get to many glucoses, many monosaccharides stuck together. They'll be called polysaccharides. So one mono, two di, many poly. The ones we're concerned about in this class are starch and glycogen and cellulose. All of these are strings of glucoses stuck together. Those glucoses stuck together are done in different arrangements. The different arrangements are related to the function of that polysaccharide. So starch for plants, glycogen for animals is a storage form of glucose. We're storing it till later. So we need to be able to put it away and then take it back out. You can think about it as the pantry. So animals can break in those bonds and access those glucoses. Hemicellulose and cellulose, glucose is strung together in a different pattern. They're put together in such a way that animals cannot break them down. So hemicellulose, cellulose, and then lignin are all part of the cell wall. And we'll pick up there next time. I have a quiz for you. You can have as much time as you want. Turn it in when you're done. You're free to go.